Thank you, everyone, for joining us on this fine evening. Adele shows me that it's beautiful weather outside. So thanks for joining us in spite of that. So tonight I want to talk about some of the patterns for building resilient serverless applications. I think before I go into that, I do want to talk about just what do I mean by resiliency, and the dictionary definition for resiliency is the capability to recover quickly from difficulties or toughness. So in other words, it's not about preventing failures per se, but to be able to recover from failures quickly. And as Amazon's CTO, Werner Vogel, famously said, that everything fails all the time. It's a fact of life, and there's just nothing we can really do about that. But what we can do is to build applications that can withstand different kind of failures that we're going to see in production, and to be able to quickly recover from them as much as possible. So, for example, in a data center, hardware is going to fail all the time. So to withstand this kind of hardware failure, we're going to run our applications on multiple servers so that if one goes down, the system continues to work. And as for the whole data center, or in AWS terms, availability zones, they can go down as well in some exceptional circumstances, like a storm cloud. And I think there was one instance a couple of years ago when I think a shark bite one of the underwater cables, and that broke down some of the network capabilities in some of the data centers in AWS. So as you can imagine, those kind of things can happen. So we are going to run our applications across multiple availability zones, or sometimes even across multiple regions, so that when one of the availability zones or regions goes down, our applications can recover quickly by routing traffic to the remaining active regions. And since the individual servers have a limited set of resources in terms of how much CPU or memory or bandwidth it has, the more user requests that it handles concurrently, the more resource we're going to end up using. And a very common failure mode is that when there are just too many requests hitting the same server at the same time, we're going to saturate either the CPU or the network bandwidth or something else, so that the latency will start to spiral out of control, which is another reason why we need to be able to scale out our application across multiple servers. And then we end up having this distributed environment where services often have to call other services, and if one of the other services goes down, then we can get this cascade failures across the entire system, so that eventually the user is going to try to do something and they're going to get the 502, and that's, of course, is not going to make our customers and our users happy, because they're going to see interruptions when they're trying to use your app to do something. And when you have a microservices environment with lots and lots of microservices, it's quite a common problem that a lot of us have to deal with in some capacity. So these are just some of the old microservices diagram from those big tech companies. I think this is about 7 years ago now. So by now they will have thousands of microservices at these companies. So my name is Yan. As Adele mentioned, I'm an AWS Service hero, and I've been using AWS since 2010. And one of the first, experience I had with serverless was 2016, when I migrated a social network to run pretty much entirely on serverless. And since then, that's been my primary focus on serverless technologies. And nowadays, I spend about half my time working with Lumigo as a developer advocate. And the Lumigo is, I think, the best troubleshooting platform for serverless apps. It gives you one place to see all of your traces, logs, and the state of your Lambda functions, and you can find errors really quickly and then drill down to the issues that caused the problem in the first place. The other half of my time, I work as an independent consultant, and I help companies all around the world go faster by adopting serverless. And so back to building resilient serverless applications, I think this is a diagram from Wui Fredrickson, which I'm pretty sure I just butchered his name, highlights the 4 broad areas that we should really consider when we think about resilience. And it's also worth considering that with Lambda, it gives us a lot of resilience out of the box already, because we have this isolated execution environment for each and every invocation. So if one user request uses up too much CPU or memory, it has no effect on any other concurrent user requests. So this is very different from when we used to run applications on an EC2 server, where all the concurrency is being handled by our code running on the same machine, sharing the same resources, and therefore, when one user request using out too much resources, it has an impact on everybody else. And when you build APIs with API Gateway and Lambda, you also just get multi-AZ out of the box, because the API Gateway and Lambda deploys your functions and your API across 3 different availability zones by default. So you don't have to do anything additional with yourself to get that extra resilience in terms of one data center goes down, it's not going to take down your app. And both API Gateway and Lambda, they also charge you based on usage. So you only pay when user uses your system as well, which is also great, especially for those low throughput environments where you don't have to run a bunch of servers across multiple availability zones and wasting a lot of CPU cycles that you just not end up using. And what's more, you also get this load balancing out of the box as well. When an API HTTP request comes into API Gateway, it's going to get routed to one of the available availability zones. And again, you don't have to configure anything yourself. You don't have to put in load balancers yourself. You just get that as part of using API Gateway. Same goes to Lambda as well. When a request goes to Lambda service, it's going to get routed to one of the availability zones behind the scenes. And if using DynamoDB, which also, by the way, gives you multi-AZ by default, I can't remember whether it's 2 availability zones or 3, but by default, DynamoDB is going to replicate your data across multiple availability zones within the same region. And you can also configure your DynamoDB tables as global tables so that the data can also get replicated across multiple regions. So now you can turn your whole API into this multi-region active setup, which is basically the gold standard for building resilient APIs in AWS. But we're going to talk about that in a bit more details later. So I guess for now I just want to say that you're going to get a lot of resilience out of the box when you're using serverless technologies like API Gateway and Lambda and the DynamoDB. But we still have to be careful and think about some of the built-in throttling at each of these services. If you think about a user request comes in, it's going to hit Rufidis 3, and then it's going to hit the API Gateway, and that's going to trigger a Lambda function that's going to talk to a DynamoDB table. So at each point along this chain, there's going to be some built-in throttling that AWS provides, and you want to make sure that all of those timeout limits and throttling is going to align correctly for your service. For example, API Gateway has a maximum timeout of 29 seconds, which is a hard limit. So even if your Lambda function can run for more than 29 seconds, you can run for 15 minutes, but API Gateway is going to time out after 29 seconds anyway. And the same goes to when you're processing messages from an SQS queue with Lambda. You have to consider the visibility timeout on the queue and how it relates to the Lambda function's timeout. The sort of rule of thumb or the general, recommendation from AWS is that the visibility timeout on your queue should be about 6 times the Lambda function's timeout. Not exactly sure how they work it out, but that's the general recommendation that the AWS tells you. A very common pattern for making your API more resilient, at least in cases where we need to do some kind of a CPU-intensive task, is to offload the task to a queue first so that the API function can respond to the caller quickly. And we can maybe give a caller some kind of a location so that they can poll and see if the task is complete. So in this case, we can do this long-running CPU-intensive task in another Lambda function where we don't have to worry about API Gateway's 29-second timeout. So this allows us to better absorb any sort of downstream problems. For example, if we need to call some third-party API, and if that API's latency is suddenly gone up, we don't run the risk of getting timed out by API Gateway because we're taking longer than 29 seconds to process a request. And we're also going to get retries through SQS. And then there's also delta queue support as well for Lambda, for poison messages. But a very common problem with delta queues is that it's all well and good to capture those poison messages, but we need to have some way to replay those events, especially if the message was failed the first time because of some temporary issue with some third-party service. So once they recover, we want to be able to just reprocess everything and go again. So AWS introduced some console functions for you to replay events from a DL queue back to the main queue, but I also have got this tool called the Lumigo CLI, which has got a bunch of helpful commands, including ability to replay events from a delta queue back to SQS queue or some other targets if you want as well. So this pattern for sort of offloading intensive work to some queue and then Lambda function is great for find and forget, where the user is going to call our API, but it doesn't have to do anything with the response, and you can just go ahead and do something else. So all it needs is some kind of acknowledgement that the task has been received, and maybe some endpoint to poll for the task response. So that's where we need to have some way to be able to respond to the caller that, hey, the task is finished. So there's, of course, there's a WebSocket, but a very common way to do this without WebSocket is using a pattern called the Decouple Invocation, where how it differs from what we did earlier is that we are going to return a location header in the initial response when the caller say, please do this task. And so we're going to give the caller a location that he can poll for the result until the result is ready. So in this case, a request is going to come into our queue, into our API. Our API function is going to put the task onto a SQS queue, and it's going to save some token in the DownDB table where the result is going to be null, as in we don't have it yet. And it's going to return a 202 with location header. And so the caller is going to be able to poll this endpoint. And in the meantime, we got this SQS function that's going to pick up the task and start working. And when the client is going to poll the result, and it's going to check, in the database, the data there's no result yet. So we're going to return another 202 and say, yep, sorry, it's not there yet. Once again, here's the location header. And once the background Lambda functions finishes, and you can save the result into the DumpDB table against the original task ID. So now we do have the result in the database, so that the next time the caller asks for the result, we can check the database and go, hey, that's done now. So now here's a 200 response with the result. So it's all pretty straightforward, but you may think, wait a minute. So doing this, we've got this distributed transaction here for the initial request, where the API function have to write to both SQS and then also update DynamoDB in the same invocation. So that means if we want to do this the right way, we need to be able to say, if one of these operations fails, we have to roll back the other. So for example, if we queued up something in the queue, but then we fail to write the token into DynamoDB, then we don't really have anything to sort of report back. Similarly, if you write to DynamoDB first, but then fail to queue up tasks in the queue, then we need to be able to roll back the first action as well. So how do we then implement distributed transactions properly? Then this is where you got things like the Saga pattern, which is a pattern for managing failures in a transaction, where each action has got a equal and opposite compensating action for rolling back. And this is I got this talk here from Katie McCaffrey. If you want to learn more about a Saga pattern, she talked about it with a really good example, where if you're implementing like a holiday booking system, you need to have this transaction or this Saga where you're going to book a hotel, and then you're going to book the flight, and then you're going to book the car rental. If any of them failed, you need to be able to roll back the other things that you've booked so far already. And given that all of these are different third-party systems that you're working with, so it's important to be able to roll them back, because you can't do them in an atomic fashion. So for each of these actions, as well as the rollback actions, we can model them as a Lambda function. And then we can use a step function to then help us coordinate the saga so that we book the hotel. If there's a seat, we're going to go to the booking the flight. And if that failed, then we roll back any change we've done so far for booking the flight. And then we're going to roll back the booking that we've made for the hotel. And then we're going to fail the transaction. Otherwise, if it's everything's on a happy path, then at the end of it, we're going to be able to finish the transaction and with the booking for the car, the hotel, and the flight. So imagine now you've got this booking input here where you're going to book some trip from London to Dublin. And the happy path looks like this, where we book the hotel, the flight, the rental, and we complete the transaction. Happy days. But if there's a failure, then we have to perform the rollback action to undo state changes that we've done, and then we're gonna fail the transaction. Again, like I mentioned, if you go to the book the hotel, but then fail to book the flight, then you have to roll back both the flight booking as well as the hotel booking before you finish the transaction in the failed state. And in many cases, we can act. So saga patterns is great, but it does introduce quite a bit more complexity and moving parts into your system. And I think in many cases, we can actually just architect the distributed transaction out of the application by using DynamoDB streams instead, where, say, the Lambda function is going to take the task and then it's going to put it into the DynamoDB table. And then we're going to rely on the DynamoDB streams to trigger another function to just take the task and then put it into the SQS queue. So that way, we don't really have a distributed transaction in our system anymore. Everything is being joined by sequential steps. And we may also say, well, you know what? Why do we go through SQS queue when we can just have a Lambda function, pick up a task from the stream, and then just do it right there and then? So that's another option as well, where we can even simplify this whole setup by just sidestepping SQS and use Lambda functions to process the task from the DynamoDB streams. One thing to consider, though, is that when you're using DynamoDB and the Kinesis streams, there's this really interesting error handling behavior whereby messages are retried until success. And so this can be very useful in situations where you know for a fact that the only thing that's likely to go wrong is when, say, some third-party system is having an outage, in which case any messages that you try to process is going to fail and they're going to get retried until success. And then there's nothing for us to do. So if the third-party system is down, then we're just going to keep on retrying in the background. And then when it's back, we're just going to pick up where it left off and just continue on as before. So that can be a really, really useful thing to have, or characteristics to have. But the thing to keep in mind here, though, is that DynamoDB streams only keeps data for 24 hours, and there's no way for you to extend that. If you're using DynamoDB with the Kinesis streams, then you do have the ability to then extend that retention to beyond 24 hours, which can be really useful in certain situations, especially for, over the weekend, if things are failing and there's no one on call, then it's easy for you to miss data or miss those failures until it's too late. So if the outages are also, if the outages are possible, it's possible for the outages to last for more than 24 hours, then we also need to make sure that we have some alerting in place so that we can deal with any issues quickly. So I think 2 years ago, AWS introduced the ability for you to change this retry and success behavior and introduce some kind of a delta queue for stream processing functions as well now. So you can control how many retries attempts you can make, and when you still can't process them after all those retries, then the messages can be recorded and sent to a delta queue instead. So this way, now you have to have some way to handle those to handle those messages that's been sent to the delta queue. And you can configure the maximum number of retries and also have the option to split the batch when it errors, because with Kinesis and DynamoDB streams, your function receives events in a batch. And in this case, imagine you got a batch of 6 records, and after the first attempt, if something failed and the function errors, then it's going to get tried again. But the second attempt is going to split the batch in half and only give you the first 3 records. And it still fails, then it's going to split again and only give you the first 1. And only at this point, you start to count the retry attempts until you hit the maximum retries. And after that, then if the message still failed, then it's going to get sent to the delta queue. Now, the very important thing to keep in mind here is that the delta queue for Kinesis and DynaDB stream functions records a message like this in the delta queue. Notice that you get the shard ID as well as the sequence number to fetch the data from the stream, but not the payload itself. So if you're not careful, you're not paying attention to this, especially when you're working with DynaDB streams, it's very possible for you to think, oh, we got DLQ, and you think, oh, everything's going to be good. But then 24 hours later, you look at this and then you realize, oh, you try to get the data, but the data has been expired from the stream. So once again, you need to have alerting in place or have some automated process in place so that when a message goes into the DLQ, you automatically go back to the stream and fetch the data while it's still there. So we talked about DynaDB and Kinesis streams, and both are batch event sources for Lambda. And the same goes to SQS as well, which is actually a polling-based service. But when you're using Lambda to process events from SQS, it looks as if it's going to be some kind of a push mechanism. And the reason for this is that Amazon actually runs a cluster of pollers that post SQS queue and then forward the messages to your function to process. And when your function returns, it's going to delete those batch of messages for you. But if your function errors, then the poller doesn't tell the SQS to delete messages. So those messages are going to get retried again. And if they keep on failing, then eventually they're going to get dropped into the delta queue. After the visibility timeout, and then the function, and then the message gets retried a certain number of times. But the important thing to note here is that the whole batch fails as a unit. So we have to deal with partial failures. What happens if I don't want to reprocess successful messages again and again just because it happens to be in the same batch as some failed message. So nowadays, what you could do in this case is configure your event source mapping for SQS and Lambda, and say that enable and in this function response types array, put a string in there called the report batch item failures, which then allows your function to say, okay, given a batch of say 10 records, 2 of them failed. So you can put the message IDs of those 2 messages and then include them in the response from the Lambda function. And this then tells the poller that only these 2 messages failed, and it can happily delete the other messages that were processed successfully. So that's about SQS and handling partial failures. So moving on to another very common problem in microservices, where sometimes doing the right thing can actually have the opposite effect. So imagine we have Lambda functions that need to call this service A. And at any moment in time, we have a number of concurrent executions all calling this service at the same time. Now imagine this service is having some problems. Some of those requests is going to fail or it's going to time out. And so to make our applications more resilient to these kind of temporary issues, we can have retries with exponential backoff built into the app. And in normal situations, this is absolutely the right thing to do. And the AWS SDK do this by default as well, except in cases where, say, service A is already struggling, it's now got to deal with retries as well as a fresh new request from other Lambda invocations. And so now it's struggling, it can't handle all the requests, and you're getting more and more requests. So more of the requests is going to fail, and then they're going to get retried again, and so on until the whole thing just kind of falls dead on its feet. So this, my friends, is what we call a retry storm, where the problem sometimes gets exacerbated by doing the right thing and retrying those failed requests. And the solution for this problem is to use a pattern called the circuit breakers, where you can have retries, But after a certain number of consecutive errors or timeouts, you're going to trip the circuit, and so that no more requests can be made to this service, and any of the attempts just going to fail outright. So we're going to throw like a circuit is open exception or something like that, and we're not going to make any request to service and give it a chance to actually recover before we send any more requests. So instead, once the circuit is tripped, we are going to only allow one request through, say, every couple of minutes, and to see if it's working now. If it works, then okay, we assume things are back to normal, and we're going to close the circuit, and we're going to keep on making requests to this service. But if it still failed, then we're going to keep the circuit open, and we're not going to let another request through until, say, another couple of minutes later. That way, we give the service a chance to recover, and hopefully, once it's back to normal, then everything resumes back to normal. So this is a very common pattern, very common practice in microservices. The big question for a serverless application, though, is where do you put the state of your circuit? Since Lambda functions, the different concurrent executions, they don't share any state. It's by design. It's great. It's one of the things that makes your serverless application more resilient. So now we can either let each concurrent execution track its own state, which is, I think, is simpler. There's no external dependency, but it does allow more requests through, since every single Lambda worker that's handling requests for your function have to independently come to the decision that this service is down. So it can be also inefficient in the sense of stopping requests going to this service that's failing. Or we can store the state of the circuit in something else, like a DynamDB table. The downside of this is that, okay, now we got another thing we're going to depend on, which if we're going to do things right, means that we should probably also have a circuit breaker on that DynamDB table as well, right? So, I mean, personally, I always try to start with the simplest solution, which I think is the in-memory approach, and then I'll upgrade to using DynamDB tables if we find that in practice that's just not good enough. And when things fail, we are seeing too many requests and takes too long to converge on a decision. In which case, taking the risk that this DynamDB table we're using can itself have problems. We just take that as a risk that we have to also manage. And then there's the gold standard of building resilient serverless applications, which I mentioned earlier, which to make them multi-region active. So imagine you've got this REST API you've built with API Gateway and Lambda and DynamDB, and they're all running in, say, US East 1, and they're sitting behind some Route 53 domain and some user-friendly name like API.myapp or .com or something like that. So now this setup is pretty resilient already, because everything has got redundancy across multiple availability zones, because that's just what you get out of the box with serverless. But you're still vulnerable to the kind of region-wide failures that we don't see often, but they do happen sometimes. So to get to that next level of resilience, we do have to go multi-region by deploying the whole application to maybe 2 or 3 different regions. And so we can serve requests from all these regions at the same time in an active setup by using Route 53 to route traffic to different regions, maybe using some kind of geolocation or latency-based routing strategy. Now, to make sure that all the data updates are synchronized globally, we have to connect the regional DynamDB tables together as a global table. And so AWS is going to handle the data synchronization across the different regions for us, which just makes life so much easier compared to what we had to do before. And finally, we have to set up some kind of a health check in Route 53 so that if one of the regions goes down for whatever reason, then traffic can be diverted to the other regions that are still active and still working automatically. Of course, this is subject to the TTL you have configured on the DNS record set, and typically that can be set to like 5 or 10 minutes, depending on how quickly you want to be able to react to things. But this approach is also not limited to APIs. So if you've got some kind of a data processing pipeline, for example, and you have the pipeline that says ingest data from some upstream SNS topic through SQS and the Lambda, and data gets written into DB tables, which is then used to support your API with API Gateway and Lambda. And now suppose your upstream system is already running multi-region, active. So you've got two upstream topics in different regions you can subscribe to. So in this case, you can subscribe your queue to both of these topics. And if one of the regions goes down, the upstream region system goes down, then the pipeline is still just going to work because you're going to get events from the other topic anyway. So Amazon engineers call this static availability, as in the system is always available without manual intervention in the event where there's a failure with availability zone or even a regional outage. However, in this setup, you do end up ingesting the same data twice in the normal path. So you have to have some kind of deduplication somewhere. This can be done using deduplication in, say, SQS, if you're using a FIFO queue, or it can be done with, say, the DB table, where when your function that's processing those events and writing them to DB, you can use a conditional update to make sure that you don't write the same data twice. But then you may still want to make sure that your pipeline itself and the whole API is also multi-region active. So what we do is we would deploy the entire data pipeline to two different regions, and we're going to set up global table for all the regional DB tables, and each region is going to subscribe its SQS queue to both of the upstream SNS topics in the two different regions. This way, again, if one of the regions fails, then the system is just going to keep on working anyway, because everything is being processed in the other region, and data is being written into a global DB table. And we can use, again, the same trick as before, and use Route 53 in front of our API, so that in the unfortunate event that the whole region goes down, not just some specific service, then the system will still just keep on working, because upstream is still feeding data to our data pipeline in the region that is still working, and the API is still working in one of the regions, and is able to serve user requests once the DNS record has been refreshed and is then pointed and routed to this active region, this sort of healthy region. So the downside of having multi-region setup is that they are just more complex. They are going to make everything a bit more complicated, from how you deploy your application to how you monitor things. They're also more difficult to test as well, especially for, how do you simulate this kind of failures cases to make sure that it actually works? I mean, on paper, everything seems fine, that if one region goes down, it's just keep on working. But how can you be sure that that's actually the case? So the best way we have for testing this kind of complex systems is chaos engineering, which you may have heard about already from the likes of Netflix or Amazon, who keeps talking about how they will, kill their servers in production at random so that they can simulate the infrastructure failures that cause EC2 instances to blow up, and see if the system can still stay up. When those kind of problems happen, is certainly one way you can apply the principles of chaos engineering in practice. But chaos engineering itself is much broader. In the words of principles of chaos.org, which is one of the best places you can go and read about chaos engineering. It talks about how chaos engineering is a discipline of experimenting on a system in order to gain confidence in the system's capability to withstand turbulent conditions in production. And it's a discipline that's getting getting increasingly important to many organizations, just because we are building more complex systems now, which has more complex and difficult to predict the failure modes. And the thing about failure is that you don't choose when they happen. As the fire chief Mike Birch said here, the moment chooses you. You can only choose how prepared you are when it does happen. And the great thing about chaos engineering is that it's not limited to just your application. It can be applied to test your infrastructure, the platform, as well as the people and processes you have in your organization by running things like game days. And also, unfortunately, Mick is not here tonight to tell you about some of the things you could do to build up this culture of resilience and of SLA, understanding of what is your target for resilience and uptime. And in terms of tooling, you probably heard about things like the Netflix Simian Army, where you got a bunch of different tools for killing servers or injecting latency or killing an entire availability zone or region. But these tools are useful when it comes to testing infrastructure. But when it comes to serverless, we don't have access to the server that's running our code, so we just don't have any servers that we can queue. And Amazon is really doing all sorts of experiments to make sure that the Lambda service itself and the API gateway service itself is running on infrastructure underneath, where those infrastructure are highly resilient, so that as a customer, I don't really have to worry about individual servers dying or hardware failures they have in the data center. But I'm still responsible for my application code, and I can still use chaos experiments to identify weaknesses in my own application. And even though, when you're using serverless technologies like Lambda and API Gateway, you do get a lot of good built-in resilience and redundancy. As we know, we talked about already, there's still lots of different ways that application can actually fail in production. Sometimes, simple mistakes like we've misconfigured the timeouts can have your user-facing API timeout while it's waiting for response from your internal functions. If, say, one of the dependencies is having a really bad latency today, and or maybe some third-party API you're calling is taking a long time to respond, or maybe I'm missing some error handling, which is, again, very, very basic mistake that we can make, but also something that's incredibly common in practice. In these cases where there's some downstream system is having an outage, maybe I could have do something in my application to use some kind of a fallback so that I can return previously received answers, and we could have cached them and returned that. Or maybe in some cases we can return a default response if we can't get the latest answer from those services, so that I can mitigate this sort of cascade failure again in the whole system, just allow our system to degrade more gracefully. So there are tools out there like Failure Lambda that allows you to inject failure into a Lambda function and run experiments so that you can see how your Lambda functions, or rather how your application as a whole, is going to react when there's some problems happening in your system. For example, I can use it to say, let's inject some errors into my Lambda function. So whenever it tries to connect to DynamoDB, it's going to get an error. So we can then test, okay, what's my assumption about how my system behaves when that happens? And then I can use that to check that, okay, it actually behaves that way. Or maybe we find out, okay, we think it's going to work this way, but turns out when we get an error from DynamoDB, it actually does this other thing instead, which we didn't expect. Then we can go back and fix the problem and make our system more resilient. Or maybe we can see, okay, what happens if some third-party API we're calling has, it's taking more than 10 seconds to respond, and then we can see how our functions actually behave, whether or not the whole error is going to bubble all the way up back to the user. And you can test out all kind of different failure modes more proactively, and then identify failures and weaknesses in your system before those problems actually happen in production, which they will eventually, because, again, everything fails all the time. And what we can do to build more resilient systems is to make applications that can withstand these failures and recover from them quickly, not necessarily to prevent them, but to recover from them. And that's everything I've got. Thank you guys very much for your attention. And as mentioned earlier, I do a lot of consulting work. So if you want to see how we can work together, go to theburningmonk.com to check it out. And I'm also running a workshop in the August. So feel free to have a look at the productionreadyserverless.com. Yeah, any questions, feel free to ping me now, or you can reach out to me on the social media later as well. How do you test your Lambda functions before deploying to AWS? Do you use something like local stack? So yeah, that's such a question I get a lot. So personally, I don't use the local stack, but what I often do is I'll make sure that I've got modularity in my code so that I can write unit tests for any complex business logic I've got in the code. But then I also run what I call integration tests, where essentially I'm running the Lambda function locally. And by running, I mean just, I've got a test that invokes the function's body. And the important thing here is that I want to check that my function is integrating with those other third-party services correctly. So I will have my Lambda function talk to the real AWS services as much as possible. So how do I do this before I actually have to deploy to AWS? So what I typically do is that with Lambda, what you can do is that you can create the temporary environment. For example, we've got your dev account, test account, staging, and production account. But within those accounts, I can also create temporary environments where I can deploy my Lambda function, API gateway, DynamDB, and so on into a temporary environment called dev.yen, so that while I'm working on a feature, I can deploy any new databases that I need to provision and the test against into AWS. This is not gonna affect anybody else because this is the environment just for me. So I can then run my integration test against those temporary environment and then make sure everything is working. And then after that, I also have the end-to-end test because integration test is not going to catch everything. There's a lot of things that can go wrong. That's to do with how your, say, API is configured with, I don't know, IAM roles, as well as if it's because, you're delegating a lot of things to API gateway, for example, for authentication and authorization. So you want to make sure that the whole thing is working together end to end. So I write end-to-end tests that actually calls my APIs from the test. So yeah, that's how I normally test things. I don't use the local stack at all. I find that with things like local stack, it just takes so much effort to set up and to get it right. And they are also quite brittle. They break very easily. And I've seen a lot of teams spend weeks trying to get the local stack working the way they want, and then suddenly something breaks, and then they spend another week trying to figure out what the hell's going on, when it takes me 3 minutes to deploy it to a new environment, AWS, and just go with that. So I hope that answers your question. Get another question here. How do you make Cognito multi-region? I can make every part of my architecture multi-region, but I can't find a solution for Cognito. Unfortunately, there's no solution right now. It's one of those big gaps that we have in terms of this whole idea of this whole dream of making things really resilient by going multi-region. But then when it comes to the user authentication system like Auth0 or like Cognito, all of these systems are single region. They still have multiple availability zones behind them, but there's no way to make them multi-region, unfortunately. There are others. I guess I've seen a lot of people attempt different ways to make this kind of work, but I think they all cause more problems than it solves. So I guess we have to just wait for the AWS to come up with something better and the native support for a multi-region Cognito. Got another one here. What about AppSync? Can you make it multi-region as well? So it's you work very much the same as you would do for API Gateway. I haven't done it myself. I haven't done this with AppSync, but the core principle is the same, where you have your DynamDB tables be global tables, so replication across multiple regions, and then you deploy the same API across multiple regions. Where you maybe get a bit tricky is if you need to do WebSocket. I'm not sure how well that works across multiple regions. So AppSync's got this subscriptions mechanism. But other than that, the sort of GraphQL operation itself, that should span across multiple regions the same way that you would do with API Gateway. Okay, got another question here. how your org or team treats reliability. Is that a technical issue only to be dealt with by the platform? So it really depends. I guess the bigger the company, some of the enterprise customers I work with, they do spend a lot more time thinking about resiliency and just in general ahead of time. Where some of my startup clients, the focus is very much on getting things done as quickly as possible. No, you won't have a good baseline, but it doesn't have to be great because the cost of downtime is not as significant compared to a large enterprise banking customer who an hour downtime can lose them millions of dollars by the minute. So I guess that cost of that return on investment is very different when it comes to when looking at different contexts. And that's also why things like chaos engineering is getting so much attention nowadays, is because some of these big enterprises, big companies, the cost of failure of downtime is really significant. So it absolutely makes sense for them to invest even heavily into better resiliency. And even if it means going from 99.9 to 99.99, which is a huge investment, but for a lot of these companies, it's absolutely worth it. Is that a technical issue? Yeah, it's not just a technical issue. It has to be something that's more of that starts with culture as well, and that's something that what the reliability guys are really focusing on. And it's a shame that Mick is not here tonight to really tell you about some of the things that they've been working towards that. Yeah, let's see. Another question here: in a serverless environment, where does a long-running task that require more than 15 minutes to finish live? So I think there's quite a few different ways to approach this. Personally, depending on whether or not the task has to be done continuously, or can you break it down into smaller chunks? Because if it's the latter, whereby I've got this one big task, but it doesn't have to be one continuous 15 minutes, but it can be 5 minutes and then 5 minutes and then 5 minutes. Then the way you could do is you can use something like a step functions to sort of drive your almost like a recursion, whereby you have some function that process, say, a large S3 file with a million tasks, and then you can keep a pointer and as to how many tasks have you processed, so that you run one batch and you run it and you check every time you process the task, how much time is left in your current invocation. And if there's less than, say, a minute left, then let's just finish this invocation and then let step functions trigger your function again with the previous pointer that you returned, so that you essentially got this recursion going on, this recursive function. Or you can, if you don't mind operating with some infrastructure, then you can use a Fargate, in which case you can just run a task for as long as you need, really. The downside is that once you get into that container environment, you have to worry about the security for the container images, as well as patching the various different things that you wouldn't have to worry about when it comes to Lambda, because with containers, you are responsible for the security of the container images you're using and the things that you're installing into those in that environment. And if you're not using Fargate, then you also have to be responsible for the security of the underlying virtual machines and networking security and all of that. So again, depending on your appetite and ability to manage those environments, you may just decide to go with a Fargate if you think, okay, yeah, we can do this. It's not too bad. We've done containers before, and we don't mind doing a little bit of infrastructure, not a huge amount. Then Fargate is probably the right answer for you.
I think that's the end of questions. Well, Jan, thank you so much for speaking this evening, and for everyone who joined us. Obviously, we're going to have to finish up a little bit earlier today. We don't have our second speaker, but we really look forward to welcoming you to our next session. So, the next meetup is out. We have a save the date for the 28th of April. It's going to be a lunchtime session where we're going to be joined by the engineering team at News UK. They're going to be sharing what reliability and building reliable and resilient systems means to them. So it'll be an open discussion for everyone that's part of this community to get involved. So head over now to the Meetup page to sign up. And obviously, if you have any feedback from the session today, or if you have a great story that you'd like to share with the community, we're always open to hearing from you. So please do reach out. And Jan, I believe that you had a number of links mentioned throughout your slides. There was a great video that you posted. So if you can get that shared on the Meetup page after, along with any of your contact details, I think it'd be great to continue the conversation. And if anyone has any further questions from Jan, they can contact you via your Twitter and so forth.
Sure, sounds good. Yeah, we'll do that.
Excellent. Great. Well, that's all from us this evening. Thank you all for joining from wherever you are joining us from. Really appreciate everyone spending the evening with us, and we look forward to seeing you at the next meetup very, very soon.